first of all, are there any questions about okay, let's say the logistical things in class? We have, there was some, and if there's any residual questions about the exam. Okay, again, I grade on a curve. I posted the mean. Some people came in with scores at you know, right around the median, and they asked if they were failing. Are they failing if they came in around the median? Okay, so again, I grade on a curve, and it's a median. Okay, median split between A minus and B plus. Any questions on the midterm? Yes. What's the standard deviation? To be honest, I don't know that I saw that, but I did give you a complete curve of the, if you went to the key assignment, you saw a complete curve of a histogram, right? And from that, you can estimate the standard deviation, right? Actually, I was thinking a great problem for a final exam would be taking a histogram like that and giving an upper and lower bound on the standard deviation based on the histogram. I'm not sure I'm going to do that. If I have to remember that thought till I get to my where I write it down. But that would be a perfectly fine question to ask, okay? So maybe you can look at that and figure it out. Any questions? Okay, okay. One thing before I forget is, just so everybody knows, next class is on Tuesday is fall break. Am I correct? Okay, so that means there is no class on Tuesday. Okay, and the last logistical thing that I wanted to talk about was the next homework. The next homework, I decided, just because to give you an extra weekend to work on it, I've delayed the next assignment's due date till a week from Tuesday instead of a week from today. Does everybody get that idea? Okay, but it doesn't mean you shouldn't enjoy your fall break working on this. But I want, you know, just, I think it's probably good that we have another class period. Any questions or comments about the homework 3? People have started playing with it. Are there any things that they wanted to, any questions, any issues? Yes? The deadline has been on, not on the 24th, on the 22nd, I believe. Can someone verify that this is true? Yes, so it's slid to give you an extra weekend, not an extra week. Okay, any questions? Yes?
The data set that we need to find in question 4, are we supposed to use it for any other question?
Okay, so there's a question of, one of the things says, I want you to find some other data set that can do something interesting to help you, relevant to this problem. And where might you use this, okay? Of course, you could use it if you see something interesting that will lead to a good plot. That would make a great visualization, right? It could be that you will use it in your models to try to predict the residual, okay? But that's what you can use it for. And if you choose not to, I don't think you'll get shot. Okay? Any questions? Yeah.
In question 1, like we are supposed to find out the top 10 desirable houses in the least 10.
Yeah.
So can you have negative desirability scores for it?
Okay. Can you have a negative desirability score? And again, a desirability score, it would feel to me, I don't see any reason why you can't have a negative desirability score, okay? Why is it, at least in the United States on the SATs, and it's probably true, it may be true for the GREs also, it used to be true, they were graded on a 200 to 800 scale. That may not still be true, but the SATs are still on the 200 to 800 scale. Why was the lowest score on an SAT 200? So I think there was a theory maybe that that's what a random paper would be, okay? My theory was always that it made people feel better than if they got a 0, yeah?
I heard it was just because they wanted to get people to show off, so like you got points if you signed your name no matter what.
Okay, so you know you got there, you got at least a 200, maybe you felt good about. So when it comes to the issue of negative desirability scores, the houses aren't going to feel bad to get a negative score, okay? So that doesn't bother me. And so whatever is you can decide what a reasonable metric is. It's good for a metric to be interpretable though, okay? And so, if I were thinking about a desirability score for houses, what might I want? If I'm going to have negative scores, 0 probably should mean something. Does 0 mean, a house, a median house? A house fit for a graduate student at Stony Brook? I mean, you need to have some, I would say that there should be some kind of, interpretation there. But there's no reason why the scores mean anything, especially because there you're just trying to sort them to find the best and the worst. It doesn't matter whether or not, we're dealing with that. Any questions? I will say, just because you got me started on this, we work with this group in the Netherlands on a lot of, statistical data. They have access to all the government statistics, and one of the things is to try to predict future income. And do people have negative incomes? You guys may think you're poor, but you probably don't get negative, you may not have negative incomes. There are people with negative incomes on their taxes. How do you achieve that? Well, there's certain things. Let's say you have a business that loses money, okay? You now have negative income. And so, things can get negative that don't obviously seem like they should be negative in life. Any other questions about the homework? Yeah.
So this type homework one, can we take top 100 or 1,000 data points because of computation?
Okay, so what is important? It's important that you, if you have a computer that is too small to process all the data there, then do something that that you can do, and think through it. My guess is for certain things, you will have more than enough processing to deal with all the houses. I have to believe that when it comes to, for example, identifying the 10 best or worst houses, I can't believe that your computer is going to be too slow to do that in a minute or two, okay? But maybe I'm wrong, once you have a formula, okay? I can believe certain pairwise comparisons and clustering might be too slow for your machine. If so, use your judgment. That's my recommendation. Certainly it's dumb if you instead keep your computer busy for 24 hours just so you can say you got the full set of points. Any questions? Yes.
So you say houses. The list is full of properties. So are we allowed to remove the ones that are not specifically like residential houses?
Use your judgment here. That sounds like what fraction of them would you say are not properties but not houses?
I didn't measure the count.
Does anybody have a sense of that? Is it 1%, 10%, 50%? Okay. I will say use your judgment. Obviously, properties are different than houses in some sense. For example, if you have an office building, how many bedrooms does an office building have? Okay, it doesn't have bedrooms, right? So use your judgment. If you decide that it makes more sense to filter out non-residential properties, I can respect that. Any questions? Okay, fair enough. Okay, so what I'd like to finish talking about today is the statistical significance testing. Okay, and we talked last class about two different kinds of significance testing. We talked about t-tests, and we talked about the KS test, the Kolmogorov-Smirnov test. I may have been a little quick on the KS test. Any questions about that? Basic idea again was you have two populations, two samples, you want to know if they're drawn from the same population. If they're drawn from the same population, the cumulative distributions of the samples should look similar. Okay? And one measurement of how similar they are is over all possible values of x, what is, of the random variable values, what is the biggest gap between these distributions? If the gap is too big, it's probably not drawn from the same distribution. If the gap is small enough, it probably is drawn from the same distribution. You can assess the size of the gap by comparing how does it compare to something that is something that's proportional to something like 1 over the square root of n, okay, and times this constant c of alpha, which you look up in a table, or probably these days by running a computer program, that will say if you want to be sure that the chance you see this level of difference by chance is less than 1 over alpha, okay, this constant times this square root n thing is going to determine what that logical distance is. Any questions about that? So this thing comes up from a test. Any questions? What happens as n gets larger and larger? How much of a difference is acceptable between the two the two distributions? Does it get bigger or smaller? If the distributions are the same, they should get smaller. The observed differences should get smaller with n. Okay? Because if they're really the same thing, the samples in the limiting case should kind of be there. Okay? Any questions about that? And again, I just say I like this test because I get a picture out of it. And so I can see why this thing is happy or unhappy with my samples. Any questions? Okay. Now, there's one very important issue in significance testing that that people often get in trouble with. Okay, and I'm going to sort of motivate it by this picture up here. This is a graph which shows as a function of year, it plots the amount of dollars that are raised by video arcades and the number of PhDs in computer science granted every year. Okay? Now, I don't know how well you can see that graph, but what is your conclusion looking at that graph? What is the seeming truth about the computer science PhD counts and video arcade revenues? Very strong correlation, very tightly linked. Does everybody see it? Went up at the same time, went down on the same time. Unbelievable correlation. And a correlation this strong on this many points is, going to come by chance very, very rarely. Okay? So my question to you is, when you see a plot like this, is it that more PhDs caused more video game revenues? As they got PhDs, they got paid more and they could go spend in an arcade? Is it that the more video games being played inspired people to go become PhDs in computer science? Is it that there was some other effect that happened in the world, global warming, that caused both an increase in arcades and an increase in PhDs in computer science? Or is there a spurious correlation? Which would people vote for? Okay, and if anybody has a preference or not. Who here thinks it's a spurious correlation? Most people. The rest of you, who thinks that more PhDs caused video games? No one. Okay, I think this is a spurious correlation. Now, why would you think? Why can I prove or suggest that this is a spurious correlation? You can't tell by looking at this plot, but you can tell by knowing how the plot was generated. The plot was generated by this author who wrote a book, which I unfortunately can't remember the name. It's a funny book filled with all of these graphics. And what did he do? He took a look at a bunch of time series, okay, a database, systematically compared every pair of these time series and reported the ones with the highest correlation. Okay? Now, if you know that this is how he created the plot, that is kind of the reason to be suspicious of the correlation. Okay? And this is an important issue to think about when you properly interpret what statistical significance means. You know, I haven't been very rigorous about it, talking about it so far. But it's important to remember what that value of alpha was. Alpha is a significance level in classical statistics. When you go back to my slide on the KS test, see there's that little alpha over here. What does alpha mean? Alpha is, you kind of, the way you test significance here is you can kind of think of this as a dialogue with the statistician who's going to judge it for you. You say, is it real that the computer scientists and the video revenues are correlated? And the guy says, what's your definition of real? What is your probability of this thing happening by chance that you're willing to accept? Okay? The significance level is the probability that this kind of result came by chance. You say, okay, I'm willing to say these two things are from the same distribution. I want to know if these two things are from the same distribution with a probability of, 0.2, 1/20th or less. That fixes the alpha, okay? And then when you do the test, what you're getting back from the statistician is, yes, this is significant at this level, or no, it isn't. Okay? So you to a certain extent have to fix this significance level to know how often are you willing to trust, let's say have a false positive come up here. Any questions about that? Now, what's the problem? Historically, statisticians said the significance level of running a test, okay, where you would accept a false positive with probability 1/20. That's a significance level of 0.05. Okay? Now, what happens when you run millions of hypothesis tests? What fraction of them are going to come up as true even if nothing's going on? 1/20th. 1/20th of a million leaves enough interesting, funny ones to write a book about. Does everybody agree with that? So if you're going to run what I would call a fishing expedition, where you're comparing pairs of things against each other and looking for a high correlation and then wanting to say, wow, you've got to make sure you're using an appropriate level of alpha in order to do that. Actually, did you guys, in maybe the previous assignment, did I ask you to build a correlation matrix of how similar pairs of stocks were? How many of these things were there? Depends upon who you were doing. It may have been 500 by 500, right? That would be, what's 500 times 500? I know it's a big number. It's a big number starting with 25. What is it? 25? Is it 2,500 or it's more than that, right? 250,000, right? Now, if one of those came back being extremely high, is that a very impressive result or not? And the answer is, it depends upon what your significance level is. It should be clear, two things should be clear now. One, that when you test lots of hypotheses, to measure them as being interesting, to be unlikely, see a strong thing and say, is this unlikely to happen by chance? You need to raise that threshold of interest. That much has got to be clear. And it's also got to be clear that computer scientists love to do fishing expeditions where they try all pairs of things and see what happens. Okay? So correcting for this is something that is the kind of thing that people like us have to be able to do. Okay? The most famous correction for multiple hypotheses is something called the Bonferroni correction. Okay? Who was Bonferroni? He was a guy who developed it. Okay? What is his idea? He says that if I am testing n hypotheses, and I want to make sure that once I specify my alpha, my level of, kind of random false positives that I'm willing to accept, okay? If that alpha was 1/20th, that's fine. If it was 1 out of 100 or 1 out of 1,000, depends what it is. If I want to know whether of these n hypotheses, any of them are good enough, I have to test them at the level of alpha over n, okay, to make it a even smaller number. And that only if it's significant at the level of alpha over n will I take it as significant at the level of alpha. Any questions about that? So sometimes this is interesting because to test something you need to know where the hypothesis came from and were there other other tests here. Any questions? So I remember once that there was a drug that people, again, drug testing is one of these areas where statistical significance is very important. And the FDA has regulations. You have to prove that your drug is better than the alternative for to at least some standard of alpha. I don't know what it is. Maybe it's 1/20, something like that. And they open up the data, and it didn't make it. Okay? And so suddenly the company's stock price dropped. And then someone said, wait a second. There's a minority group here. If we take just the people from our minority group here and we run the test on them, look, this is significant to the level of alpha. It helps people in this minority group. Now let us sell the drug. And the FDA said, no, no, no. Yes, it's now at this level of significance, but now you have used a second hypothesis, right? And in order for this to count, it's got to now rise to that level divided by 2. And it didn't make, okay? And the company, lost money, went out of business. It was a happy ending. Okay? Any questions about that? Okay, good. Okay? Okay, so what does statistical significance mean? Okay, I want to say that there's kind of like 3 different things statistically we can think about when we think about we do an experiment. Usually there's a correlation which measures how much one variable predicts another. Significance will tell us that that there is some kind of relationship between these two variables that was unlikely to happen by chance. Okay? You know, and if you have huge numbers of samples, very small numbers of very small differences in populations can register as as highly significant, unlikely to occur by chance. That doesn't necessarily mean that it's really an important effect. It just means that it's a real effect. So like one example that I kind of like is, do men or women have more fingers? Who has more fingers on average, men or women? Who here thinks it's men? Who here thinks it's women? Few people. Who here thinks that it's the same? Okay, well, the answer is it's not the same. Depends, and actually, it's interesting is it depends upon actually how you count it. Men are more likely to play around with power tools historically, and tend to get fingers cut off in, in lawnmowers and things like this. Okay? Actually, women genetically seem to be more prone to getting extra fingers by some kind of a mutation. Okay? Now, are these significant results? The answer is yes. Does everybody in this room have 10 fingers? I believe so. Okay, I don't want to put anyone on the spot, but it's highly likely you all have 10 fingers, and it's highly likely that there is a significant difference between the average number of fingers on men and women. Okay, and the reason is if you use a large enough size, a very small difference can be very significant, can be real. So what you really often care about is something called effect size. Not is the difference real, and how sure am I that the difference is real? The question is the difference of a large enough magnitude that it should make, that I should care about it? Okay? And so there are some statistics that you might find to see whether the difference in the populations are meaningful or not, okay, or the similarities between the two populations are meaningful. The fact that the populations are the same, or something and something else is highly related, okay. So the correlation coefficient we know goes from -1 to 1. Social scientists tend to think that when you see a correlation of something at about 0.2, they sort of call that a small effect. And a correlation of about 0.5 is a medium-sized effect. And a correlation of 0.8 is something really large. Okay? So again, if we think about the predictability as being something like r squared, a correlation of 0.2 affected something like about 4% of explained 4% of the variance in one population. Okay, that's small, that's thing. In distributions, we can start to say how much of an overlap is the distribution. You guys are used to seeing, histograms. The overlap here of the histograms for two populations would be, the degree of as a measure of how similar those two distributions are. And again, folklore sort of uses these kind of boundaries to judge whether effects are small or large. There's a statistic called Cohen's d, which people use, which is the difference in the means divided by the standard deviation. A bigger difference means the difference between the two communities is large. And how to interpret that thing is in terms of the number of standard deviations. Any questions about that? It should be clear that significance means there's a real effect, okay? You know, effect size measures how interesting or important it is. Any questions? Okay. What else can I tell you about? Now, the thing that I don't like about statistical tests, okay, again, I kind of like t-tester, I do like the KS test, okay? I do use it and I tend to trust it. But what bothers me about statistical tests, and probably is that they tend to be somewhat opaque. They were all developed around the turn of the early in the 20th century. They have rigorous definitions and assumptions that they're based on. So there is a theory here, but and it's based on ideas like what should happen when you draw from given distributions with specified means and standard deviations. You want to know, you have tools like Bayes' theorem that convert from what's the probability we see this data given the distribution. Okay, we can all convert that to things like what's the probability of the distribution given the data. Okay, so I find these very opaque. That doesn't mean that they're wrong, okay, but it's something that causes me a certain level of anxiety when I use one of these things. Often there are different assumptions. There's a reason why people are trained as statisticians, because there's some subtlety in doing these tests. So what I'd like to talk about for the rest of what I hope is going to be the rest of class is a different approach to establishing a confidence of an observation you get that I do like and that I do kind of trust, okay? Because I do kind of visualize it and it's a computer science-y kind of thing, okay? And it has to do with a idea of doing random sampling, okay, and running experiments in some sense to see, let's say you see an observed effect. I guess at one point we talked in here about we had sampled a bunch of men and gotten their IQs, a bunch of women and gotten their IQs. Is this a real difference? Okay? Now, one way to approach this computationally, where I don't have to rely on looking something up in a book or using some statistical test where there are subtleties. Is the test one-sided or two-sided? Is there an assumption? A lot of these tests have a built-in assumption of one of the distributions has to be normal or something like that. We can use something called a permutation test. And what I like about permutation tests are that they are computational, and they are idiot-proof in the sense that they reduce to, if you have a program without bugs, you should come with a way in believing something without external things. So I like permutation tests. Okay, so what is a permutation test? And I'm making you do one on the homework. So I want you to take a look at this thing. So what is the situation? Suppose you have a hypothesis that is true. Suppose you think that, let's say, men are, you have one where you think women are smarter than men, and you think your data proves it. Why? Well, I took 10 men and 10 women. I took their, I computed the average IQ of each group, and men were bigger. Women were bigger. Okay? Fine. So now let's take your data and scramble it randomly. Meaning, maybe I'm going to hold the names of the genders the same, but scramble up what the IQ values were. Okay? Maybe that's what my picture is going to be here. Okay, this was a different. Okay, let's just take a look at this example here. Maybe it'll be clear. This was actually for weight, height, I think, or weight instead of IQ. But let's just keep with the story. Let's say we are given a bunch of women, and these are their measurements. Here, I guess. Okay, let's say it's height, because we do believe women are shorter than men on average. Here we've got a bunch of men. This is measuring their height, right? And we could compute the average woman height is probably about here, right? The average male height is probably about here. Looks like the average male height is bigger, okay? Should I be impressed with that, okay? One argument is, what if I hold the genders the same, but now permute, randomly scramble the height numbers, okay? Now, if you look at this thing, I've now got every one of the original height values that I had is still in this data set, okay? But some of them had sex changes. Does everybody see that? Okay. What fraction of them have had sex changes, by the way? If we randomly scrambled these things. And let's say there were the same number of men and women as before. What fraction of them had sex changes? Yeah? About half of them. Okay. And now, if I now take this new sample and I sort my pseudo-women, my randomly created women, and my randomly created men, okay? Now I've got another distribution. And I could take the average height of my pseudo-women and the average height of my pseudo-men, okay? Now, if men really were taller than women, it should be the case the difference between my real men and my real women in height should be greater than the difference between my pseudo men and my pseudo women. Does everybody agree? Now, what if I do this 100 times or 1,000 times, right? I can randomly scramble this thing as many times as I want. What am I going to get every time I do that? I am going to get a distribution. It will probably be normal, normal-ish, okay? I mean, a bell shape, let's say something like this, right? And now when I do this, I've got a histogram of among pseudo men and women. The difference in their height, okay, most frequent is around 0, which is probably what I would think, because they're now, kind of, just equally likely to be of any gender, right? Sometimes we get very tall pseudo men. Sometimes we get very tall pseudo women, right? But now, suppose I take a distribution and I compare it to the actual observed distribution I saw. Okay? This purple line represents, let's say, the real value of the difference between the men and the women. Right? In this case, which let's say maybe was IQ, the real women scored as smarter than the real men. That's why the difference is negative, right? Should I be impressed by how much of a difference there was? Okay. Well, if I randomly relabel it, 100 times, and I see this level of skew or bigger, let's say 30 or 40% of the time, that's not very strong evidence that this difference I got in the real data set was real. Does everybody see that? Not sure I'm seeing that now. But if I got something like this, where I had a height difference I observe on average of being this, And in all my random samples, okay, the pseudo men versus pseudo women difference was much less than that. That is a sign that this kind of a difference was unlikely to happen by chance. Does everybody get? That's kind of what the significance test we're trying to get at is. How likely am I going to see something by chance? My claim is that the fraction of random samples which score better than the observed thing is kind of measuring my significance level of how likely am I to see this by chance, right? In this case, I did 100 examples. All of them scored less than this one. So what's the odds of me seeing this by chance? Probably less than one in 100, right? In this case, I had 38. It looks like I had 38 examples that were where the women were even pseudo examples where the women were even smarter than I observed in here. What's the likelihood that the evidence for women being smarter is real? If it's only 38 out of 100, I'm not very impressed, right? So the great thing about these permutation tests is they give you an experimental way to tell whether or not, help you judge whether the effect you're seeing is a real effect. Any questions about that? Okay. So what do I like about this, just to make sure about it? Basically, the problem of doing a permutation test requires exactly two things. It requires me to have a statistic measuring the difference between, let's say, my two populations, or the similarity of my two populations. Perhaps it's the difference between means. Perhaps it's the correlation of something. Okay? And I need a way to construct random permutations, okay, in a way that is truly random. Any questions about that? Once I have that, I can plot my distributions, I can see where the real thing lies, and I get evidence whether it's real or not. Any questions? Okay. So what is the idea, some of the nitty-gritty here? It should be clear that the more permutations you run, in principle, the more impressive your significance is. Okay? If you can run 1,000, that's better than 100. If you can run 10,000, that's better than 1,000. Right? It gives you, the more independent permutations you run, the more refined your significance, and the more you can measure extreme, ultimately really where is the strength of this thing. Okay? It's important that when you permute things in a way that you're basically permuting the value of a column. Okay? Typically, you want to permute one of the columns, the target variable, let's say. Randomly scramble that, keep the records themselves the same. Suppose, let's say, I had my data record had things like the the height and the weight, and I'm trying to use that to predict health or something like this. Scrambling the target value of the health is a fair thing. Scrambling the components of the data record that you're going to build a prediction from doesn't seem as good, because if I take people in here and you have heights and weights, and from this I want to compute a health statistic like BMI. If I permute the heights, then the relationship between heights and weights has been lost. And if that's not the test that you want to be making, okay, then that's the wrong thing to do. Okay, so there needs to be some judgment here and some clarity of thinking about what you want to test. Okay? Any questions? One thing that permutation tests are good for is if sometimes people have models and they say it's great, if I feed it randomized data, permuted data, and it still is great, that's a sign that your model, something's wrong in your testing or something like that. Okay? Any questions about the idea of the permutation test? Okay? So I think this I like because I see it and I understand it. Now, statisticians sometimes get unhappy with permutation. I mean, it depends on who you talk to. Okay? With a permutation test, if you think about it, let's say that I had my IQ, women and women's IQ test. What was I measuring? I am kind of measuring something about what is the probability I see this skew, given the idea that there shouldn't be any skew between men and women. Okay? Now, statisticians are typically really interested in what is the probability my hypothesis is true, given the data. So, in some sense, the contingent of what you're trying to prove with a permutation test is reversed. Okay? But I think that permutation tests give you a good insight into whether something is working or not. Okay? And I do encourage you to do it. And I'm telling you to do it on the assignment here. On the assignment, I'm asking you to predict you're going to build a model to try to predict the difference between the Zillow price and the actual price a house sold, right? That's kind of, I think, the noise in, in kind of the Zillow model. I think it's not obvious that everybody here is going to be able to do anything with that. It might very well be the best predictor you have won't be able to make a really impressive prediction over random chance. The permutation test gives you a way to tell if I see a improvement in error of 0.0265. Is that interesting or is that not? That's an example of this kind of subtle test that a permutation test can come up with. Any questions about it? Okay. One operative question here that's interesting is to do permutations tests, you have to be able to construct random permutations. How do you construct a random permutation? Okay, I want you to give me, how many permutations of n things are there? N factorial. What does a random permutation mean? It means it gives you one of those n factorial permutations with each one of them with probability 1 over n factorial, right? How can you construct a random permutation? Can anybody give me a computational method to do it? So one idea is, which some people would do, is to say, if I want to get a random permutation of the numbers 1 through n, you're saying draw samples from a normal distribution. What if I have a random number generator that gives me real numbers from one to another? Okay? If I associate each number with a random number drawn from 0 to 1, let's say, or equivalently from a normal distribution if it's really random, what do I then do? If I sort these records by the values of this, the random numbers I generated, what's going to happen? Does everybody agree that that should scramble all the numbers from 1 to n? And if I really had a random number generator that I could trust to generate numbers at random, this would give me a way to do it. Does everybody see that? How many people see that? Okay, what's the running time of this method? N log n, you know how to sort, plus whatever God knows what, well, it's constant, presumably, per random number you get. Okay? Now, there's a better algorithm for constructing random permutations, which is one of these two that runs in order n time to construct a uniform permutation. What does it do? It starts by loading an array, an n-element array with the numbers 1 through n, right? Then what are we going to do? We're going to do n minus 1 swaps, okay? Where we start with take the element that's currently in the ith position and swap it with an element in a randomly chosen position, okay? Any questions about that? Okay, does that kind of make sense that if you start with an array here and you take the elements and you swap them with randomly chosen elements from the array, you will come up with a random permutation? Now, which of these algorithms is right and which of these algorithms is wrong? Okay? I show you two random permutation algorithms. Okay? First of all, are they any different? Okay? Can anybody see a difference here? One has an I and one has a 1. Okay? Can anybody think which one of these generates the permutations? So what's this thing saying? This first one says swap the ith element with an element to the right of it. Right? That's kind of what this thing is doing. When I is 1, swap the first element with an item to the right of it. Okay? The second one says swap the ith element with an element picked randomly throughout the entire array. Okay, you see the difference? Does it make a difference? Should it make a difference? Okay, which one's right? Okay, who has an opinion? Who here thinks the first one is right, where you swap to the right? Okay, one person. Who here thinks the second one is right, where you swap it with everybody? Okay, you're thinking it's more random if you're swapping with everybody, right? And the answer is you're wrong. Okay? Why is it that the first one is right? Okay? Anyone have an argument about that? First of all, let me convince you that it makes a difference. Okay? This is what happens when you run the two algorithms on 1,000,000 random permutations for n equals 4. How many permutations are there for n equals 4? 24. What would we want our permutation generator to do? To look like this, where all permutations occur with roughly equal frequency. Are they going to occur with exactly equal frequency? No more than if you flip 100 heads, it's guaranteed 50 heads and 50 tails, right? There's going to be, but it should be close. The red line is what happened where you pick the other spot arbitrarily at random, okay? Any questions about that? So it's clear that there is a real difference here, okay? It also should be clear. Yeah, question? I thought you had it.
I was going to say that, I don't know if this, for me, like with the algorithm 2, it seemed like you could just like undo swaps that you like done before.
So the difference between algorithm 1 and algorithm 2 is that you can undo swaps that you did before. That's certainly true. Now, is it clear that that hurts you? Not immediately clear to me. I mean, if I'm walking around and trying to do with this, can I prove that that's wrong? Not so obviously. But I can prove that the first one is right. Okay? What is the argument that the first one is right? Okay? What is the probability that a sub 1 is every one of, what is the probability of all n elements ending up in the first position? It should be clear that for the first element, the first element has to have a probability of 1 in n for every one of the n elements, right? Because I'm swapping 1 with one of any of the positions from 1 to n, equally likely. I'm picking one, I'm putting it there, okay? And that element could have been any element equally likely, right? And it's never going to move again to solve your problem. So I know that that's right. What about the second element? Well, recursively, I'm now going to be doing the same thing, okay? So the second element is now also equally likely to be every one of them. So this turns out to be right, okay? For the second one, actually last night I worked out for myself, because this is subtle, okay? I worked out to myself that like if you have a permutation of length n, the probability that the second element is not going, that 2 is going to be in the second position is not the same as being in the first position, okay? But that's a case analysis and things like that. So what's the lesson here? The lesson here is random sampling is very subtle, and you have to get it right, or else you will get weird effects from things. Okay? Any questions about that? Okay? This is good to feel in your heart, because this kind of problem comes up often and often again. Okay? Any questions? Okay. Let's look at a random sampling question, because I do think random sampling is a thing that people have to be able to do for computational experiments to validate things that are important. Suppose I ask you that I want to get random points within a circle. Here, you guys look at this. This is a circle. Okay? I'm going to say that's a circle. Okay? And suppose I want you, it's a circle of radius, let's say 1/2. Okay? That's the radius. Okay? R equals 1/2, I guess is what I should put it out. Something like that. How do you, let's make it radius 1. Sorry about that. That's dumb. What is the, what is a procedure to randomly sample points within a circle so that they are uniformly, so you get random points inside a circle? Does anyone have a procedure in mind? Okay, you.
I can take every pixel and with a head-tail coin toss, I would either mark or do not mark the point.
Okay, what I think you're saying is treat a picture, I heard the word pixel, you're saying put a pixelation on top of the circle, and then pick every one of the spots equally likely. You know, we flip a coin to decide which spot you take. Okay? Maybe. What are problems with that? Yeah?
Obviously, you have some pixels that are not in the
Some pixels are not in the circle. Some pixels are partially in the circle. Okay? So there's some level in which I don't like this pixelization idea. Not necessarily terrible. What's your idea?
You just uniformly generate your angle
Okay?
or your radius.
Okay, what's another idea? Okay? The other idea is, no, not a square here. He wants to think about a circle. The other idea is that we know that every point in a circle is specified by an angle theta and a distance from the radius, right? Theta goes between 0 and 360 when I was growing up. Now it seems to go between 0 and 2 pi, right? Okay? And the distance goes between 0 and 1. Okay, does everybody agree? That now reduces to picking two uniform random numbers. Which of these samples on my screen was generated by that algorithm? You want it to be on the left because you wanted this to be random. You wanted to look like that. That's a beautiful random sample, right? You're not happy with this random sample, are you? This is what came from your algorithm. Now, why did it look like this? Can anybody figure out why it looks like this? Okay? And can anybody see why it has to look, it looks like this? Yeah?
Yeah, I think, so let's just take like the radius is 1, and then you kind of like take the circle inside it, radius is half.
Yeah.
So that circle will have like 1 by 4 the entire.
Okay, so the thing is, think about what's happening at the radius of a half. What fraction by that random sample, what fraction of that points are going to have a radius of less than or equal to 1/2? 1/2 of them, okay? But what is the area of the circle? This is, I guess, pi r squared, right? This is what? Pi big R squared minus pi little r squared. And if I remember correct, that's about 3 times as much area in that outer annulus that there is in the center, right? So this random sampling algorithm produced that. His random sampling algorithm would have produced something a lot closer to this, okay? But there was something discrete in his flip every coin that I didn't like, okay? What is the way that I would be doing it? The right way to be doing it is something called Monte Carlo simulation. What if I put a box around my points, but not a grid? He wanted to put a grid, okay? And I now randomly pick my x between 0 and 1, and my y between 0 and 1. What do we know? Every point is either going to be in the box, in the circle, or it's not in the circle. How can I decide when a point is not in a circle? Distance from the center, okay? And now I can take every point, okay, and test whether it's in the circle or not. If I keep shooting these random darts at it, okay, they will be uniformly distributed within the body of the circle. Any questions about that? Okay? Yeah.
Would it be possible to like vary I guess like the distribution across because I said like uniformly generate your like radius. So would it be possible to sort of generate the radius by a different distribution such that?
Okay, so now one way to save this in some sense would be if you could come up with a distribution of the radius to look at so that you, if you came up with a distribution on the radius, so small radiuses were rarer than they were under the uniform distribution, okay? And probably with a little bit of calculus, you could come up with what that distribution is, right? Now you got to know what?
Probably x squared.
Maybe it's n squared. I'm not, I don't want to think while I'm standing up, but I might believe that, or something like that. And this now requires you to think, and it requires you to be able to sample randomly from that distribution. Does you kind of get that idea now? Now you're telling me, no, there is some weird radius distribution that I'm proposing. I'm sorry, I don't have a better chalk here. I tried to get one earlier. I've got some weird radius, probability distribution that I am trying to sample from. And now you've reduced your problem to that. So we need to now be able to generate samples from a weird distribution, and then we could save your idea. Does everybody agree? Okay. That provides a good insight into why, in a minute, I'll talk about how you sample from weird distributions. Okay? So keep that in mind. Why does this method of Monte Carlo sampling work well here? Okay? If we think about it. If I ask to sample in a circle, okay, this clearly is a good thing. Now suppose, let's say, we had a weird shape. Are weird shapes going to be good or bad by this model? Let's say I want a shape within a, I want a sample within the body of a squid. Okay? Randomly sample. What makes this harder? Well, first I still got to put a box around my squid. Okay? Then that's fine. What do I need to do? I need to be able to test whether my point is inside the squid or not. Right? What else would make this worse for the squid? Even if I had a method to test if it's inside relative to the circle. Yeah.
The fraction of area that's outside the squid is not the same.
The problem is this is a squid that's been on a diet. Okay? And the squid doesn't take up very much of the box. Does everybody see that? The ratio between the area of a circle and a square of radius 1, of diameter 1, is pretty much the same. If I had something where the bounding box, let's say the worst thing would be, suppose I had a diagonal cigar, okay? Almost all the bullets I fire would be in vain. Okay, that's the limitation of random sampling here in weird shaped regions. Any questions about that? Okay, so that's good. Now, how do I solve his problem though? He's saying, what if instead of a uniform distribution, you guys kind of, I think, believed you could sample from a uniform distribution, right? How do you know that? Well, I've used a random number generator that tells me it's generating numbers from 0 to 1. That's one reason you believe it. Does anybody remember how they generate that, though? There are these methods called linear congruential generators and things like that. There's ways of doing it that I don't really want to tell you about. That you can look up. But how can you sample from a weird shaped function like his new radius function that might be quadratic? Okay? Well, what if you take the PDF of this function? Let's say the weird function you wanted to generate was from the normal distribution. The normal distribution is still weird to me compared to uniform distribution. How would I sample numbers from a normal distribution? Well, what if I compute the cumulative distribution function of the normal distribution or your weird shaped distribution? Now I have a, a function where the x range is the same and the y range is 0 to 1. What is the right way to deal with this? Okay, hopefully I can draw it here. What if I now pick a number uniformly from 0 to 1 and treat that as the y? Kabunk. This was my random y. It's between 0 and 1 uniformly. What I now want to do is to go, hopefully I can do this. Go back and ask myself, what is the cumulative distribution value where, I know what the cumulative value is. Now, suppose I go back to that thing, okay, there will be a unique x value associated with that cumulative value of y. Does everybody kind of see this thing? Once I am dealing with a cumulative value, I have basically all possible values of the normal distribution spread out, so that I can, and I can sample uniformly in the probability, and for any probability between 0 and 1, it maps to a unique value in the CDF, okay? I can then go and look this thing up. Okay, and this gives me a way to do the random sampling. Any questions about that? Perhaps looking it up, if it was a weird enough function, maybe I'd build an array with a lot of values, maybe 100 or 1,000 values, and then randomly sample to look it up which box in the array I should be going to. Okay? Or I could interpolate or something like that. But this gives you a generic way of doing this. Any questions about that? Any questions about random sampling? It should now be clear how a p-test how a permutation test works. It should be clear how to generate random permutations, nice and neat. And while we're at it, we should be humble and check out any random number generation or random sampling thing to see that we really did it right if we thought they were generating it in a uniform way, because it's very easy to make mistakes here. Any questions about random sampling or p-test? Yes?
So if we wanted to take the radius, like the previous problem, from a weird distribution.
Yeah. Okay, right.
Instead of sampling it from like a random distribution, a weird shape like that, should we just take from a uniform distribution?
Well, the uniform distribution is what he was doing. He was saying, just pick any R. And the trouble was that if you pick any R, half the points, the radius will be R less than a half, which is fine. That's true. But if you want, but it's not true that half the points in the circle have a radius of R less than a half. So you're not sampling them uniformly. Okay? This is a big problem. There are, hedge funds that have gone broke because they thought they were doing random sampling right, and they weren't doing it right. Okay? This is a subtle thing. Any questions about that? Okay. Any questions about random sampling or this? If not, I got 3 minutes. I'm going to confront you with something different. So, last chance. Okay, let me just try one thing I want to show you, just because you're going to be starting to make, after this we're going to start, how do I get this thing off? No. Okay. One thing I just want you to think about quickly, which maybe I'll show you here. I took a look at all the, you guys submitted plots on homework 1. And you submitted plots, and you're going to have to submit interesting plots on homework 2. I want you to start to get sensitive to what is a good plot and what is a bad plot. That's what we're going to talk about in visualization. You don't have a class on Tuesday. Next Thursday, we'll start talking about visualization. But these are plots generated by people in the class. If you see, some of them will be what you may think are good, some are bad. I want you to be art critics and tell me something. Here is a plot on correlation matrix. Is this a good plot or a bad plot? Does anybody have a feeling here? Who here thinks good plot? Who here thinks bad plot? Okay, you didn't like the guy who did it, right? It's a personal thing. Why do I think it's a good plot? A good plot tells a story. Okay? Do I see something here? What do I see? What do you see here? I don't have to be the one telling a story. What do you see? Yeah?
I can see
These 4 companies seem to be higher correlated than most. And this pair seems to be unusually strongly correlated. And now, why do you see this? Okay, well, these arrows represent, they happen to use something that did some clustering, an agglomerative clustering procedure, which we'll eventually talk about in here, but rearranged the companies to show this effect. Why is this? The companies here are Citigroup, Wells Fargo, JP Morgan, Bank of America. Why is there a strong correlation here? What? They're all banks, right? If it's a good day for one bank, it's a good day for another bank. Why there's a strong correlation here? One of these is ExxonMobil. One of these is Chevron. Why is that strongly correlated? They're oil companies. If it's a good day for an oil company, it's a good day for another oil company. Okay? By rearranging this, you see something. Here is another plot. What do people like about this one or not? Okay? Does anybody have a... Who here likes this one? Who here doesn't like this one? Okay, here we're trying to guess what my answer is going to be. Okay? What do I see here? What do you see here? Is there anything you see in this? Yeah? Okay, so there are grids of pairs of companies that don't seem to... What's interesting? There do seem to be these blue bars representing companies that are weakly correlated with everybody. That's probably interesting to look at why that is. So that is something I'm seeing here. Okay? Now, why don't I see other company things listing here? It's because the companies are ordered by alphabetically rather than by sector. If I organized the companies by sector, you would see blocks and you would start to better see these things. And this, I think I'll stop for you now. Well, next time I'll show you a few more from the class, okay? But I want you guys to start thinking about what makes a plot that tells a story, doesn't tell a story, that you can learn something, don't learn something. And we'll talk about it next Thursday. Okay, take care. I will see you guys. And if you haven't picked up your exam, you can come and get it from me after here. Thank you.